session of COSI Training School, and the session is devoted to quantum dots. So the first speaker will be Andrij Baumketner from Lviv University. So Andrij, you're here, right? You can share your screen, and the floor is yours.
Okay, thank you very much. Can you see my screen now?
Yes, we can see it.
Yes, we can see presentation. Everything is fine.
All right, thanks a lot. I am not actually from university. I work at the National Academy of Sciences. But
okay, so I apologize.
I was in university before, but that was 20 years ago. Anyway, let me first apologize for not having video because my laptop computer broke and I'm connecting from work. Secondly, it's a pleasure for me to give a lecture at the summer school. When I was a graduate student, I attended quite a few summer schools, and it was always fun, especially visiting foreign places like Trieste, for instance. Unfortunately, Kyiv now is not the best place to visit, but hopefully that will change in a very short time. And secondly, third, please interrupt me if you have any questions as we move along. Don't wait until the end of the lecture, because I don't mean this to be just a regular seminar or other section in which we can interact. And so my topic today is lead halide quantum dots, and that's a problem that we have been working on for the last 10 years. And I will present some results, but the focus and emphasis will be on methodological perspective, on algorithms and on methods that we use and which make these studies of quantum dots possible. Few introductory slides. So what are quantum dots? Nanoparticles with specific optical properties, in particular well-defined forbidden band that depends on the size of the nanoparticle. So these nanoparticles can range from few nanometers to 20, 30 nanometers, and as we change the size, we can change the band gap, and therefore we can change the color of the light which these materials can emit and absorb. It's a relatively new material, but has been reaching advanced stage lately and has already managed to make a big impact. For instance, in 2023 Nobel Prize in Chemistry was given to Mungi Balendi, Louis Bruce, and Alexei Yakimov exactly for the development of quantum dots. And there are plenty of applications that you can envision, both in which quantum dots emit light, like QLED displays, and where they absorb photons in photovoltaics, for instance, for light detectors and so on. Lead halide quantum dots are the most recent addition to the family of quantum dots, and it has certain advantages like very bright emission and very narrow emission lights. On the structural level, all of these lead halide quantum dots have perovskite structure, which is shown here on the left, and the main features are octahedra, where lead ion is inside and surrounded by 8, in our case, bromide ions, but could be any other halogen ion, such as chlorine or iodine. In addition to these 2 ions, we have a third ion, cation, which could be cesium, could be formamidinium or something else, and it depends. The structure slightly varies with the chemical composition, but the emission spectra depend a lot on that. And so here we have a whole series of spectra that can be generated by very for instance, by replacing cesium with formamidinium, etc. And so what is important about these structures is that they are ionic, so they are completely made of ions, and there is very little change in electron subsystem. Typically, these quantum dots are grown by mixing precursors into a jar with solvent, and then the material has very small critical nuclei, so it starts growing crystals immediately. And then this process can be stopped by either temperature jump or just exhausting the precursors, and in the end, we will have a whole lot of small nanoparticles, but interestingly enough, these nanoparticles have almost crystalline structure. If we were to try and use these nanoparticles for some applications, we would have a problem because they are not stable. So like I said, the nanoparticles are made from ions, and if you place them in a non-polar environment, like shown here, so they will start interacting because we use the dipole-dipole moments, and so they will precipitate very quickly, and there will be no useful application for them. On the other hand, if you place them in apolar, in a polar medium like water, then the polar molecules will start interacting with the ions and perhaps ripping them off the surface and eventually leading to the dissolution of the nanoparticle in the medium. And so that's a big problem with stability, and but luckily it can be solved by using surfactant ligands. And surfactant ligands have two types of chemical groups. One group is polar, and it's called head, and the other group is non-polar, and it's called tail. And so head groups will interact with the nanocrystal, try to attach to it, and cover the nanocrystal in a layer that will have like a hydrophobic or non-polar corona around it. And so when you place such object in non-polar medium, it will be already screened by ligands, and so there will be no strong attraction. Actually, we can choose how much attraction these particles experience by modifying the length of the tail, which is typically like an alkyl chain. And so we can tune the effective interactions between these nanoparticles and even make them self-assemble into various superlattices. So this is now a very hot topic where we can try and make bigger structures from these nanoparticles. Now, if you place such an object in polar medium, then you'll see that these hydrophobic groups will create a protective layer, and the polar molecules will have a hard time penetrating it and reaching the nanocrystal, and therefore the interactions with the polar molecules will be diminished, and therefore the nanoparticle will be stable. So that's in theory how it's supposed to work. In practice, everything will depend on the nature of the interactions between nanoparticle and the ligand, and these interactions are actually critical to the stability. In the older days, where nanoparticles were made from some semiconducting materials, the ligands were designed to be chemically bonded to these nanoparticles, and so the protection was then guaranteed. However, it's a very complicated and advanced synthesis protocols that are required to bind these ligands to the nanosurface. In the LHP nanocrystals, the interactions are not covalent. We have ionic, perhaps bonding, perhaps some electrostatic interactions, and we need to be able to control them carefully in order to achieve stable nanostructures. And so the question of how to design these ligands is central to the stability, and there is a very wide range of options that we have at our disposal if we want to synthesize a new ligand. So first of all, it may have charged or neutral head, for instance, cationic or anionic ligands. It may also have a dipolar head, or might have a head that is composed of two charge groups, so-called zwitterionic ligand. All of these options are available, but what we need to know is how exactly these ligands interact with the surface. And for experimental methods, this is a tough question to answer, but not so much for theoretical. So what, in theory, we would like to know about these ligand nanoparticle interactions is, number one, what is the mode of that interaction? Basically, what is the structure of the ligand on the surface? And right away, it's easy to imagine that you could have a head group that is lying on top of the crystal, or it can displace one of the ions that is already part of the nanoparticle, since these nanoparticles are not chemically bonded. And so that's a possibility. The second question that we'd like to know is how strongly these ligands bind, because the stronger the binding, the better the stability of the nanoparticles, and so we want to be able to screen against this binding energy. So these two questions we will try to answer, and like I said, by experimental methods, it's not very easy to do because of various limits that the methods have, primarily the lack of atomic resolution, but also a whole lot of other issues. So from simulation point of view, everything seems easy. The nanoparticle that we are interested on the range of few nanometers across, so we can place them in a simulation box that has, for instance, 10 nanometers across. And then we will end up, if you fill that box up with water, not water, some other solvent, I'll talk about that later, then we will have about 500,000 atoms, less than 1 million atoms. That's not a very large system by today's standards, but the difficult part is equilibrating the system. So the characteristic time scale over which these nanoparticles assemble is something on the order of milliseconds and more, could be even hours. But what we can cover on computers is on the order of 100 nanoseconds. And so right away we have a problem, even if we try to simplify the description that I showed you before by just considering a surface on which we try to deposit a ligand. So we can reduce the size of the system, but it does not help with the time scale. And so why is that time scale so relevant and difficult? Let's see in this example. So imagine that we have a system where a ligand is absorbed on the surface, and then we can view this as a two-state problem. Then we'll have a bound state with certain criterion and an unbound state. And for each of them, we'll introduce probability from which we can calculate free energy. Therefore, when we take the difference, we'll have a free energy of binding. And typically, we know that the free energy is about 100 kJ per mole. Now, if we go back from this delta F to probabilities, we will find that PB, for instance, probability of the bound state is going to be 0.9999, many more nines, and the probability of the unbound state is 0.0000, something 10 to minus 10. Yeah, so eventually, when you set up a simulation like that and hope to see that the ligand will unbind and then bind again, so this is not going to happen. So typically you have a trajectory where you see one unbinding event over many, many years. And therefore, just straightforward simulation is not going to be very helpful. And so you need to do something else. We've been researching algorithms for this problem for quite quite a while, and I'll give you an overview what we have found works and what we have found does not work. Basically, what we need is enhanced sampling approaches, which broaden the scope of the problems which can be addressed by computer simulation. So what I'm going to do next is to introduce some basic math that we need to understand these advanced sampling techniques, and then I will give you a few examples. So the starting point for us is going to be distribution function in the canonical ensemble P of gamma. Gamma is just a point in the configuration space, and beta is the inverse temperature. And P of gamma is exponent minus beta gamma up to some normalization factor, which is known as the partition function. Is there a question or someone muted? So if we look at this expression for the partition function, it's an integral, and so we can play a trick here, replace exponent minus beta u with the representation for delta function. So you see, if you integrate, you will get back the expression from which we started. And now we can change the order of the integration, put the dE in the first place, and then we will have an expression that looks like this. Integral over the gamma of delta function E minus U of gamma. So basically this integral is zero wherever delta function is zero, and is non-zero only on the contour that corresponds to the energy level E. And so you may recognize this as a familiar function known as the density of states. So here is the definition. And so density of states in mathematical terms is nothing but the surface area of the hypersurface that corresponds to the given energy level. And so the partition function then can be cast as an integral, or more conveniently as a sum over all different energy levels, exponent minus beta E with the density of states. And so the density of states turns out to be a very important quantity. It, for instance, defines the distribution function of E, which can be measured, for instance, in simulation. So if you write out the expression for that distribution function, and you see that the delta function pops up here, and then you can replace it with N of E. When you know N of E, you can calculate P of E. And that is important because you can, for instance, vary beta in this expression. And so from just one single function N of E, you can calculate P of E as a function of temperature. On the other hand, if you don't know N of E, you can use this expression to evaluate it. So you can invert this, and you'll see that N of E is proportional to P of E, which can be measured in simulations, times exponent beta E. And so that's a very important and useful function that is used a lot in analyzing simulations. Now, we can extend this notion of the density of states to multiple parameters. For instance, if we introduce one more parameter, which we can call x. And so we will follow the same procedure. Introduce delta functions now for energy and for that x. And then since these two parameters can be coupled, we have to introduce a two-dimensional or joint density of states, energy, and x. And then the distribution function is just that joint density of states times exponent minus beta E. And so one important property of this joint density of states is that it can be used to define distribution function of parameter x, so shown for instance here, and then it's going to be just the sum over E exponent times density of states. And so when we sum over all E's, we can introduce a new function called T0 of x, And that P0 of x is going to be just a non-normalized distribution function of the parameter x at certain thermodynamic point given by temperature. Now imagine that we are dealing with a problem where we have very slow relaxation, and for instance we have identified the source of that slow relaxation is a variable called x, so-called slow variable. Now if we go back to the representation of the distribution function here, we see that if we apply additional potential, so we have the original form plus some additional potential which depends only on x, for instance, right? And then we substitute this into the formula for the distribution function and do some math. You'll see that the part that depends on x will be factored out, and so we will have here sum over e, which will only give us x. And so we'll have x here and x here. And as a result, the distribution function in this artificial ensemble defined by external potential is going to be the original potential, original distribution, sorry, times this factor, which if you plot it, will look something like this, where xi is the maximum. And so it looks like umbrella, therefore the method is referred to as umbrella sampling, times exponent fi, where fi is a normalization constant associated with this external potential in basically defined by parameter alpha. And so now you see that we can design a system in which the maximum in the distribution appears at the position xi. And so if we study a problem where this black dot is interacting with the surface very strongly, so we can apply harmonic potential and pull the particle away from the surface. And so in that way we can explore the entire configurational space, which wouldn't be accessible otherwise. The problem now is that what do we do with that distribution pi? Because eventually we want the unbiased distribution. And so the way to obtain that unbiased distribution from the biased one is through so-called weighted histogram analysis method. And I'm not going to go into detail, just briefly tell you that we can introduce a number of these points, xi's, which are called windows. And then we can record histograms or distribution functions from these different windows, and then combine them in a procedure that is designed to minimize the error with which the density of states is determined. And that gives us a set of equations which are known as the Venn equations. And so we have two ingredients in them. Pi is the bias distribution functions, and Fi are some as yet unknown parameters, and alpha is the parameter that we plug into our system ahead of time. And so this equation 1 gives us the reweighted histograms for the original system, and the second equation is how these parameters Fi are connected with P0x. And so these two sets can be solved recursively. From a given choice of f, we can calculate P0. From P0, we can calculate f, and then go back and iterate until we see convergence. At the end of the day, we obtain distribution function P0 of x, which we can normalize and obtain the unbiased canonical distribution for the variable x. Now, this distribution function by itself is interesting because it tells us what macroscopic states our system is visiting, but it also can provide information on energy of different macro states if x can be used as a parameter to define that. And so imagine that we can fix a variable x and calculate some average force that is associated with it. And so these brackets here in average. And then the work that this average force will execute when we make a small displacement delta x is going to be fx times delta x. And if we convert that work to free energy, so it's going to be negative. And then provided that this function is integrable and is a full differential, we can make an argument that we can integrate this function f of x and obtain some sort of a equivalent of potential energy, but now it's a free energy because it's average is integrated over average force, not the real force. And so it turns out that this potential of mean force, so-called the integral, is directly related to the distribution function p of x, which we derived in the previous slide. And so here is, by definition, what p of x is. So it's a delta function of the distribution d gamma. And then d gamma is just the volume differential, which we can try and represent in a different system of coordinates. So if we transition to this different system of coordinates, then we will have to write down d gamma 1 through d gamma n, and let's say that x is 1 over new coordinates, and then the remaining n minus 1 coordinates will be dx2 times dxn, but we'll have to add a Jacobian of transformation. And so then if we transition to that system where x is one of the unknown variables, and we can collapse all of these other variables into the gamma x, we'll get an expression like this. And so here now we can introduce z of x as a conditional partition function that corresponds to the system where x is fixed. Okay. Now average force by definition is du over dx. Again, we substitute the delta function here and then make some transformations. We'll arrive on an expression that looks like this. And the first part is due to derivative of u, but the second part is due to the derivative of the Jacobian of transformation. And so that second part can be reduced to some function p average of x, but the first function can be shown to be beta fx x z of x. So eventually, if we assemble everything together, we will see that f of x, potential mean force, is equal minus kt d log of the x over the x plus the Jacobian part. Now, if that Jacobian part is 0, which is often the case, now we see that f of x is minus kt log z of x, which is essentially up to a constant log of p of x. Therefore, we can use p of x, which we obtain from simulations, as a way to measure free energy differences between different states defined by that variable. For instance, delta F between states x2 and x1 will be logarithm of px2 divided px1. So this Jacobian transformation is an important function. It should not be neglected out of hand. Sometimes it can make measurable contribution. So let's see how this works for some examples. So let's take, we have a three-dimensional case. A particle is above the surface described by potential u, x, y, and z. And so z is our chosen order parameter, and it's already part of the differential, so there is no Jacobian of transformation. So we measure p of z by our method delta function exponent, etc. And then at the end we get potential mean force equal minus kt logarithm p of z. And so if we were to obtain this probability function from somewhere, could be analytical calculation, then we would have f of z that looks like something like this. And so from this picture alone, we can determine the free energy differences between bound states and unbound states. So delta F from this curve can be evaluated provided that z is the proper order parameter. And what happens if that is not the proper parameter, we'll see here. So let's go back now to one-dimensional case and imagine that our free energy profile of PMF looks something like this. So we have two states, x1 and x2, and then we go back through our derivation, obtain the free energy difference as logarithm px2 over px1. But now let's imagine that we don't know ahead of time what this variable x is. It could be some other quantity that we figure would be a good order parameter, but we don't know exactly if it's a good order parameter or not. And so, for instance, let's say we have misjudged our parameter x and used parameter y, which is x squared. And so from simulations, we can calculate the distribution of y and plot the free energy, so like a function of y, and we will have two minima. And so then it's easy to conclude that these two minima correspond to stable states, and therefore we can measure free energy difference. But let's see what this delta Fy is going to be if we use this specific example. So the transformation of distribution function P of y is governed by the standard method, which is basically Py dy is equal Px dx, and so from that expression we can calculate what Py is actually going to be. And so now we can plug it into this delta F. We get Py of y2 Py y1, and then we'll have a product of P of x times square root of y square root of y2. And so then we see that this first part will give us the correct free energy, but then will also be this additional term, which is non-zero and which will bias our estimation of the free energy if we don't choose the order parameter properly. So this should be kept in mind when we do simulations and trying to measure different free energies. So now, how this method of so-called umbrella sampling works, we tested it a few years ago for a series of ligands that differ by the head group. And so basically we had ammonium group where all three hydrogens are present, and then just substituted one hydrogen or two hydrogens and so on. And we measure the potential mean force for the system pictured here. And so the graphs that we obtained shown here, and we clearly see what the free energy of binding is. And therefore we can compare this free energy of binding and draw conclusions regarding properties of the head groups that either increase or decrease the free energy. And so we can make conclusions regarding the quality of the head groups. So what we found is that it's extremely important for the head group to be very small. In that case, we have the largest free energy, but also the dissolution cost is large for certain head groups which allow polar molecules, in this case acetone, to bind. So these two factors have to be taken into account when we design new head groups for ligands, and basically these findings were corroborated by the experimental results. Now, with PMF calculations is just a starting point for us, and we soon discovered that it's not always right, and primarily because it has some internal limitations associated, first of all, with poor convergence, and the surface itself can undergo reconstruction when the ligand is starting to interact with it, and so we cannot capture that process just at room temperature. But second of all, the technique itself may not produce the proper results. So here is one example when problems may arise. So imagine that you have two-dimensional system where energy surface looks like this. So these black areas are all minima and the white area is the maximum. And so we are trying to investigate it by applying umbrella potential along variable x. And so this is the window in which our external potential allows our system to move. And then we scan along X, and that's the initial point, and then we move that window up, up, and up. And so eventually the phase space that we cover is going to be here, here, and there. But as you can see, we will never be here. And so we will get an incorrect estimate of the potential mean force because we were trapped in the kinetic minimum. And so you have to remember that this can happen when you apply these confining potentials. And so the way out of this problem is to either equilibrate better, and I will explain later on how to do that, or just don't use the umbrella potential, try to use something else. And so the method to better equilibrate the systems we use is so-called extended ensembles techniques. And the basic idea in them is something like this. So imagine that we start from the canonical ensemble. I showed you this function before. So beta was parameter and u is the variable. Now we can pretend that beta is a dynamic parameter that characterizes our system as well, and introduce some variable function rather that depends on that beta and characterizes my new ensemble. So in my new ensemble, extended ensemble, the distribution function P star now has a dependence on beta and gamma. And so the partition function now will contain a sum over gamma R and over beta. When we run the summation over gamma, we will end up with a distribution function of temperature or beta. And so that distribution function will look like this, where z of beta is just a standard partition function for the fixed temperature. Now see, when we divide this P star of beta, evaluated at beta 1, divided by P star of at evaluated beta 2, we will see that the z star, which is the difficult function to evaluate, will drop. And what will be left is just a combination of temperatures and constants alpha, which we know, and z beta 1 divided by z beta 2. And these two functions, as you can probably have guessed, are related to the free energies of our system at temperatures beta 1 and beta 2. And so when we convert this into free energies, we'll get that the free energy difference basically can be expressed as a sum of these alphas and betas, and then the logarithm of p beta star beta 1, p beta p star beta 2. And so these are nothing else but the distributions of temperature, and these can be measured in simulations and plugged into the formula to estimate the free energy differences. So that's the method of so-called expanded ensembles, also known as simulating tempering, and has been introduced for a while now and is very powerful when we want to cross over potential energy barriers. And in essence, we vary temperature as we go in our simulation and then measure the distribution of that temperature, and from that calculate the free energy differences. For one system, the algorithm may look something like this, but there is also a more advanced version of it when we try to simulate n number of systems at a time, so also called replicas. And for these replicas, we again have the distribution function formulated through the idea of the extended ensemble, but now we swap these copies simultaneously, and so have to work out the criteria for doing that. But in the end, we will end up with an algorithm where temperatures are not fixed along the trajectory, but are allowed to vary. And so you could see, for instance, that if you start at T min temperature, then over time you may go up, then may go down, may go up, may go down, and eventually you will explore much wider conformational space, because at high temperatures your relaxation times are much faster. And so this method is known as the replica exchange, and it's is used by us to better equilibrate the systems. And here is an example how this can be used, applied to deuterionic ligands. Deuterionic ligands have one positive charge and one negative charge, and they developed a substitute for cationic ligands because they are better soluble and they are producing much more stable nanoparticles. The complicating thing is that now we have many more states because we have more charges on the head group, but also we don't know exactly what the surface of the nanocrystal is going to be because we don't know how to do that, how to study that in experiments. It's very difficult. And so we, for this ligand, we first established the nature of the surface, and I'm not going to go into details because I'm starting to run out of time. But the important thing is that we established so-called phase diagram where on the x-axis we have ligand concentration, on the y-axis we have the concentration of the anion, the formamidinium, in this case not the cesium. And so we have an area where the stable structures, stable surfaces are observed. And so for these stable surfaces, we ran the replica exchange, which allowed the deuterionic ligand to detach and to attach to the surface repeatedly. And then we measured what the conformations are and counted how many we have in different parts of the configuration space. And we found 4 different binding, so-called binding motifs where they differ by or whether the head group displaces an ion from the surface, or the head group is just lying atop of the surface, or displaces 2 ions, etc. And so that graph for different binding motifs suggested that the main conformation is one in which the head group displaces 2 ions from the surface, and then the conformation of the ligand itself looks something like this. This binding mode was confirmed in reader experiments, so we had pretty good confidence in it. But then when we looked at that configuration, we noticed that the positive, the ammonium-based group is slightly above the surface. And then we figured out why that happens, because we already know from cationic ligands that the head group has to be small in order to fit into the hole. And so it suggested that we do a modification of the head group. Instead of this methylated ammonium, we just use the primary ammonium and perform the simulation to confirm that it actually is embedded into the surface much better. And in wet lab synthesis, returned stable nanoparticles, which turned out to be much more stable than the ones that we started from. And so eventually we were able to synthesize a much better nanocrystals based on the information that was obtained from our simulations. Now, with that method, replica exchange, we made a lot of progress, but still we could not measure the free energy difference between 2 different ligands because it's not the sampling is not sufficient. And so as a next step, we designed another scheme in which we try to measure not the absolute free energy of binding, but the relative one. And so here's the idea. So if we cannot measure how, for instance, this blue dot binds to the surface, then we can put that blue dot in competition with, for instance, the yellow dot. And so we can set up a system that has equal number of both. And some of them are detached, some of them are on the surface. And then just let the system equilibrate and see what happens after some convergence. If the blue dots are expelled into the bulk, then we know that they are better binder to the surface. Otherwise, we have the yellow being the better binder. So by measuring the probability of seeing these ligands on the surface, we can judge about their quality. Again, we cannot determine the quantitatively the differences, but at least we can tell which ligand is better, which is worse. And so we apply this technique to a series of the head groups that are based on sulfonium ion instead of ammonium ion. And so the chemical structures are shown here. And the example of what happens in those simulations is shown here. So we have two alternative runs. In one of them, all ligands are on the surface, and on the other hand, in the other simulation, they are all above the surface. And so after about 200 nanoseconds, we measure what is the probability of seeing the ligand on the surface, and we compare that probability between two trajectories, and we see that there is a convergence and there is an agreement between them. And so that simulation suggested that, for instance, in this case, the sulfonium ion-based ligand has the same binding property as the ammonium-based. And we repeated these simulations for the remaining heads and obtained a ranking in terms of their binding strength, as is shown here. And then we also synthesized these ligands in the lab and compared the so-called survivability of them against washing cycles, and basically we obtained very good correlation with our simulations, suggesting again that the binding strength is important, is basically the key property for the stability. Again, trying to improve the methods again, and finally getting the quantitative comparisons between different ligands, we developed another technique for measuring the delta F. And so that method relies on the combination of replica exchange, which allows us to equilibrate the system better, especially the structure of the crystal, and the umbrella potential. But now umbrella potential is going to be formulated in arbitrary form. So let's imagine that we have some system, again, ligand trying to bind to the surface, and over time it will detach and then attach and so on, and we can measure probability distribution function of P of Z and then convert it to the potential on mean force. And so imagine that that potential on mean force looks like this, and so we have a system governed by energy E in producing this PMF. Now imagine that we will simulate a system in which U is supplemented by the energy term obtained from that PMF. So U minus U PMF. And since these two terms match exactly, the distribution function of Z in theory should be flat. So the ligand should be traveling up and down from Z min to Z max totally at random, and sample multiple times all different conformations that it wants to occupy when binding to the surface. So the idea is then how do we derive this potential UPMF if we don't know it ahead of time? Worse than that, we are not able to compute it because the system is trapped. And so the answer is to use iterations, and it's very similar, the derivation is very similar to what is done in so-called multi-canonical ensemble, where the same idea is applied to energy. And so let's again say that we have the variable x, and we apply some external potential U of m, and it produces a modified distribution function P of m. And so that distribution function is given by this expression here, where n P of x is the joint density of states. So again, this we recognize as a P0 of x unbiased distribution function times exponent minus beta u of x. And so let's say now that my u of m is given by certain approximation at step I, and so it produces pi of x. Again, from here, it's going to be this times exponent minus beta u of I. And at the next iteration, pi plus 1 of x is going to be the same, except that u now is going to be I plus 1. But now, if we substitute p of I from here into here, then we will express p at I plus 1 as p at the previous step I times exponent minus beta delta u, where delta u is going to be some change of the entire function, the energy function. And so now, if we, in the limit of large I, want to obtain a flat pi plus 1, so it's going to be a constant, and therefore we can invert this expression. Something happened here. I don't know what happened, but you see, log p of I plus 1, log pi minus x minus beta u delta u of x. So if this is constant, we can then express delta u of x from this formula, and it's going to be kt log pi of x. Okay, and so now you have delta u. You can calculate from it u I plus 1. From u plus I plus 1, calculate another pi plus 1, and you keep doing these recursions until you get flat distribution. Actually, it doesn't have to be that flat. Enough, it suffices that the system is not stuck. But eventually, this u of I in the limit of large I is going to be u of PMF of I. So in theory, it should be converging. In practice, you don't have to achieve that perfect convergence. Now, how to implement this algorithm in practice, and we find it very useful to use expansion in half parabolas. So it's not a very common thing.
Hello, we lost the voice.
Sorry. Can you hear me now?
Yes, yes.
Hello? Okay. So it turns out that we can approximate pretty much every function by expanding it into half parabola. So half parabola looks like this. You have a minimum here, and then it goes up to a certain point, and so the formula is like this. And so if you get a bunch of these parabolas, for instance, shown here on the left. So you have parabolas upwards, parabolas downwards, and it looks like a mess. But imagine that you add them up, and the result is going to be the curve, the green curve that you get on the right. And the red dots are the results from our simulation, which we are trying to fit. And so there is a lot of noise in them, but it's okay, because we are not using that distribution for the calculation of forces. We just use it to parameterize this fitting function. And so with the set of about 10 half parabolas, we are able to approximate pretty much every shape of the potential looming force. And so here is an example of one. And here are some results that we obtained. We again do the replica exchange for the range of temperatures from 300 to 1600, and just to show you what happens to the crystal at the temperature of 1600. It does not melt yet completely, but it develops lots of fluctuations. Some of the ions are trying to detach, some others are moving on the surface like crazy, and so it's not really crystalline anymore. It's in some sort of a fluid state. And so that's good for us because we want to be able to capture the effect of the ligand on the surface. And then we add solvent. We study two solvents. One is cyclohexane, which is the solvent primarily used at the stage of the synthesis of the nanoparticles, and then a mixture of acetone and toluene, which is used at the stage when these nanoparticles are purified. So both of these stages are important for the production of the nanoparticles. And we measure the potential lumine force. And so here is an example. That's guanidinium head group and the alkyl tail. And the shape of the function is like this. It has basically two main minima, and one at small value of the distance z, and it corresponds to the head group being embedded in the surface of the crystal, and the other minimum corresponds to slightly larger z's, and it corresponds to conformations where the head group is attached to the surface of the nanoparticle. And there are some small other features that probably correspond to the solvent, but we don't think they are very important. And so this curve tells us a lot about interactions, basically everything about the interactions of the ligand with the surface, including the binding free energy, which in this case is going to be about 8 kT, and it looks like configurations where the ligand is on the surface are slightly more favorable than the configurations when it's bound to the surface. We then calculated these potentials for a variety of systems and a variety of solvents, and here I show the results for sulfonium-based ligands, the green line, and the guanidinium-based ligands, the red line. And the graph on the left is in the acetone toluene solvent, which is slightly polar, and then you see that guanidinium has lower free energy of binding, about 8 kT, while sulfonium is higher, about 12 kT. And so we can conclude from this graph that the sulfonium is a better binder. But then when we repeated these calculations for cyclohexane, which is fully non-polar solvent, the free energy of binding has gone up almost 4 times. Now it's about 45 for guanidinium and about 38 for sulfonium. And so now we see that the quality of these ligands has reversed. Now the guanidinium has a stronger binding property than sulfonium. And so again, we have multiple minima, basically 2 minima that correspond to the binding modes, and which survive actually when we change the solvent, but the order of the binding strength changes. And so what that tells us that we should not be focusing so much on the binding strength of a single head group, because its quality may change depending on the solvent. So we can design a very strong binder for the synthesis stage, but then when we try to wash the nanoparticles, they will all degrade. So there has to be a middle ground where ligand has to perform well in both solvents if we want to obtain stable nanostructures. Okay, and my time is almost exhausted, and so here is a quiz for those who did not fall asleep in this presentation. So imagine that we have the potential UPMF. Now, how do we get from that simulation with that additional UPMF? How do we get to the unbiased distribution P0 of X? And so that's what you have to work out, and then tell Serhiy, and Serhiy will tell me. Okay, so let me now finish. My group is based in Lviv, and we have a number of graduate students and even undergraduate students who are working with us on this project. And we also collaborate with a group in Zurich at ETH. where we have both experimental and theoretical collaborators, and we are supported by a number of agencies, such as National Foundation for the Basic Research in Ukraine and the Swiss National Science Foundation. And thank you for your attention, and thank you to the armed forces of Ukraine, which are keeping us alive while we are able to enjoy our pursuit of science. Thank you very much. If you have any questions, I'll be happy to answer.
Thank you very much, Andrij. Okay, so the floor is open for questions from audience in Zoom.
Probably some questions here. Does somebody wants to ask? Actually, I would like to ask Piotr if it is possible.
Yeah, sure.
Andrij, thank you very much for such interesting and deep presentation, such interesting lecture, very interesting results in different for different systems, and this methodology that you use for umbrella sampling to obtain potential of mean force. It is really interesting, and in the end, as for me, I would like to see the comparison with the experiment. So this interaction energy probably you can compare with some experimental results. So this is in some experiment, I don't know, maybe colorimetric measurements or other experiments. Do you have such comparison?
Yeah, the thing is that it's very difficult to measure solvation energy, so free energy differences in actual experiments, and that is not only related to experimental problems, but also some theoretical ones, like difference in the ensembles that you use to extract. So there is a number of ways, one of which relies on solvability, from which you can guess what the free energy difference is going to be. But to tell you the truth, we are not able to make a direct comparison, for instance, for delta F with experiment on quantitative level. What we can do is to make a comparison on qualitative. And so if we see that a ligand produces nanocrystals that can be washed, for instance, 10 times, yet another ligand only 5 times, then we know that that first ligand is much better than the second. And so our simulations then can look at the binding energy of the two ligands to see if the first ligand has a higher free energy of binding. And so we can compare them the relative free energy of binding. And in that respect, we have agreement on qualitative level with experiment. But then we can also determine the microscopic reasons why one ligand is better and why the other ligand is worse, and what can be done to improve its quality.
Mm-hmm.
So qualitative level is okay. Quantitative, it's challenging to extract. Well, it's not easy, it's not difficult to extract from simulations. It's difficult to extract these quantities from experiments.
Okay. Thank you.
Are there any other questions from audience or from Zoom participants?
I don't know if there is no question, so maybe I would like to ask another one question. This is related to the technique that you show. This is extended ensemble. Very interesting method. As for me, I would like to understand if I am correct. So this is ensemble where you change the temperature during the simulation, as I understand. Or
exactly.
So this is not non-equilibrium system.
Actually, it's not. It produces canonical ensemble for any given temperature. So here is a typical run. So this is just a time trace of temperature for the given system. So it goes up, so we can have some digitalized levels of temperature from 0 to something higher. And so then you see jumps up and jumps down. But then when you run average for the given level, for instance here, for this given temperature, it reproduces the canonical distribution. So if you collect data for the fixed temperature, it already is reweighted. You don't have to do anything else. You simply get the proper average and everything else from that. And that's the beauty of this technique, that it not only allows you to escape from potential energy minima by raising the temperature, but it also gives you the proper ensemble. And so there is nothing else that you have to do. In this particular implementation, you need to know this constants alpha, which could be difficult to design, can be done in iterative manner. But if you transition to this multiple copies ensemble, so-called replicas method, you don't have any arbitrary constants anymore. All you have to do is to give yourself a number of replicas, number of copies, assign temperatures, and then run it. And then these will try to exchange temperatures periodically. For instance, at this point, they may exchange or may not exchange. You have for that proper criterion derived from importance sampling. But eventually, over time, they will all travel up in temperature, and then they will travel down in temperature. And so if your system is trapped in a local minimum here, then it can be released from the local minimum when it visits high temperature. And then it goes down to low temperature, explores minima with lower energy and free energy. And in that way, it equilibrates much faster. And we, in the older days, I used to do tests. And for instance, for the reaction of making a dimer out of two peptides, I registered like 100-fold acceleration due to this method. And that is very significant if you have options of waiting 1 minute and 100 minutes. That's not a big deal. But if it's 1 week and 100 weeks, it's quite a different story.
Thank you. Thank you very much.